Hello students, welcome to EPG Pathshala. I am Gaurav Gupta from Sharda University. Today we are going to talk on module Inventory Models Instantaneous Replenishment from Paper Operations Management. This chapter would help students to understand application of non-instantaneous replenishment model, assumptions of economic production quantity EPQ model, and calculation of optimum batch size and minimum total inventory cost. Introduction. A fast food restaurant sells a fixed quantity of particular kind of burger to customers. A supplier of buns supplies number of buns every day depending upon the fixed number of burgers. The burgers are provided in batches depending upon demand. On the other hand, same restaurant continuously produces french fries to sell with each order. The production is continuous as instead of burgers being ordered in batches, these french fries are ordered continuously. Thus, the major difference between two production processes is that one product is produced and supplied in batches, whereas another is produced and consumed simultaneously as it is used continuously because of its high and continuous demand. Economic order quantity model was used to answer questions of how much and when to order in first scenario, whereas economic production quantity inventory model would be used to answer same questions of inventory in second scenario. Non-instantaneous replenishment model economic production quantity. Non-instantaneous replenishment model economic production quantity EPQ. Understanding of EPQ model becomes necessary in order to manage inventory of products which are produced and used simultaneously at a constant rate. For instance, in a continuous production line involving dressing of doll, two processes of putting up sock and the shoe are done in a sequence. In such a process, one doll enters the system, its sock being put up and then goes to process of putting up a shoe. At the start of process, only one doll moves along the process. After finishing off process at one workstation, it moves forwards and is preceded by another doll. Thus, products enter and leave one by one in sequence rather than being provided in one full batch as well done in EOQ model. This is the reason this model is also termed as non-instantaneous replenishment, as when a specific number of units, whether one or more, are produced, they are provided for usage. Out of the produced units, if a few are used, then remaining becomes inventory. Assumptions of EPQ. Number 1. The demand for the item is uniform and constant. Number 2. The production of an item start immediately as stock level reaches zero at constant production rate, that is P. Model is applicable only in situations where production rate is either equal to or greater than usage rate. Uniform production rate P is greater than uniform demand rate D. For instance, if demand rate is of 100 units daily, then production process should be able to produce either 100 or lesser number of units per day. Units are supplied to inventory at constant rate. Instead of inventory being built with constant size of Q units after a particular time period, it gets built at constant rate in continuous fashion. For instance, in EOQ model, a batch size of 50 was supplied after fixed time period when daily demand was of 10 units. But in EPQ model, only 10 units would be supplied per day to fulfill demand of 50 units in 5 days. Any gap between production and usage rate is constant. For instance, if production rate per day is 100 units and daily demand is 10 units for each day, then inventory would be built at 100 minus 10 equal to 90 units per day till production level is reached. After production run, number of units in inventory are consumed or used at constant rate. For example, if at the end of production run of 3 days, inventory buildup is of 100 units and daily demand is of 10 units, then only consumption will be carried out at constant rate of 10 units daily. The demand for the item is certain, constant and continuous. Lead time is fixed. Holding cost H per unit time is constant and does not change for different order quantity. Ordering cost O per order is constant and does not vary with number of orders. No stock outs are permitted. Calculation of EPQ. In the model, during the production run, demand diminishes the inventory at constant rate while production adds to inventory at constant rate. As discussed, it has been assumed that production rate would always be either equal to or more than usage rate, so there would be continuous build-up of inventory till the production run. When the production run is completed, units from build-up inventory gets used up till zero level is reached. The entire process is then repeated again. The cycle is illustrated in figure 1. With the understanding of above mentioned assumptions of EPQ, following procedure is adopted for formulating the quantitative formula for calculating number of units to be ordered per batch and total cost. As discussed, total cost would be function of only ordering and holding cost. Notations used in the model are D annual demand, H holding cost per unit, S ordering or setup cost per order, Q batch size, P number of units produced daily, T production time, D daily demand. Understanding from figure would help to understand calculation of EPQ. Suppose a batch size Q equal to 300 units are required daily, P equal to 100 units are produced out, of which 10 units D are consumed each day. Thus production time would be 3 days T, in which total of 300 units would be produced. So on day 1, 100 units are produced and 10 are used. Remaining 100 minus 10 equal to 90 units are stored in inventory as shown by A. Similarly, on day 2, another lot of 100 units are produced and 10 are consumed. Remaining 90 becomes part of inventory, making a total of 180 units as stock after day 2 as shown by B. Lastly, on day 3, last batch of 100 units is produced and 10s are consumed. A total inventory of 270 units are shown by C is formed. This whole process is shown in the shaded region, indicating process of both production and consumption. It needs to emphasize that maximum inventory levels denoted by I max is of 270 units and not 300 units. After completion of production run, the stock of 270 units is being used as constant rate of 10 units daily shown by downward moving line. This shaded area indicates only consumption with no production. If there would not have been any daily consumption and only production of 100 units, then stock buildup would be of 300 units as shown by dotted line and indicated by capital D. When this stock is fully consumed, then cycle is repeated again. Understanding of process as modeling in figure, calculation of holding and ordering cost is done as under. The calculation process is discussed for two cases. In the first case, production and consumption time period in the given year are different. In second case, formula is modified when production occurs for each demand day. Case 1. When production is done till production run. Holding cost. Maximum inventory at the end of production run. I equal to P minus D into T. In above case, production time is of 3 days, which have been calculated as Q upon P. Thus, I equal to P minus D into Q upon P. Average inventory between time t equal to 0 till stock last equal to I max divided by 2 equal to P minus D into Q upon 2P. So annual holding cost equal to H into Q upon 2 into P minus D upon P. Ordering cost. Number of orders equal to D upon Q. So ordering cost for each order equal to D upon Q into S. Thus total cost equal to holding cost plus ordering cost. Total cost equal to H into Q upon 2 into P minus D upon P plus D upon Q into S. To find minimum possible cost, the above equation is differentiated with respect to Q and simple minima calculus is applied to find out batch size Q, which would be Q equal to root of 2ds upon H into root of P upon P minus D. This formula of Q would provide manager the most optimum batch size that should be ordered with minimum total annual cost. Case 2. When production is produced every day till completion of ordering cycle. In the above reduced formula, it was assumed that production and consumption time periods are different. In the first phase, production and consumption happened simultaneously for first 3 days and then only consumption happened for remaining cycle time. But in case of product is produced daily for entire cycle time, at same time usage of product produced also happens daily, then formula can be modified to suppose a production facility operates for 250 days per year. If daily demand for the product is D, then annual demand can be computed as D equal to 250D or D equal to D upon 250, where D is annual demand. Similarly, if product is produced daily for 250 days, the annual production denoted by P would be P equal to 250P or P equal to P upon 250. Putting these values in the lot size and total cost formula computed in case 1, we get total cost equal to H into Q upon 2 into P minus D upon P plus D upon Q into S. Q equal to root of 2ds upon H into root of P upon P minus D. The formula is almost similar with changes in daily production and daily demand to annual production and annual demand. Practical example. Example of case 1. A plant manager must determine the lot size of a product that has steady demand of 30 units per day. The production rate is 190 units per day. Annual demand is 10,500 units. Setup cost for the production run is 200 and holding is 0.21 per unit. Plant operates for 350 days per year. With this information, calculate economic production lot size, total annual cost, time between orders or cycle length, production time per lot. Solution. Annual demand D equal to 10,500 units. Daily demand small d equal to 30 units. Production per day P equal to 190 units. Setup cost S equal to 200. Holding cost H equal to 0.21 per order. Economic production lot size root of 2ds upon H into root of P upon P minus D. Q equal to under root of 2 into 10,500 into 200 upon 0.21 into root of 190 upon 190 minus 30 equal to approximately 4874 unit. Total annual cost TC equal to H into Q upon 2 into P minus D upon P plus D upon Q into S. Total cost equal to 0.21 into 4874 upon 2 into 190 minus 30 upon 190 plus 10,500 upon 4874 into 200 equal to approx 862. Time between orders TBO or cycle length TBO equal to Q upon D 4874 upon 10500 into 350 days per year, approximate 162 days. Production time per lot T equal to Q upon P equal to 4874 upon 90 equal to approx 26 days. Thus per cycle production and consumption simultaneously take place in 26 days. Example for case 2. Given annual demand D equal to 6400 units, ordering cost equal to 100 and holding cost equal to 2 per unit per year, compute the minimum production lot size for each of the following production rates. 8,000 units per year, 10,000 units per year, 32,000 units per year, 1 lakh units per year. Also compute EOQ and compare the results. Solution. Q equal to root of 2ds upon H into root of P upon P minus D. Root 2 into 6400 into 100 upon 2 into root of 8000 upon 8000 minus 6400. It becomes 800 into 2.23 equal to 1784 units. B with 10,000 units per year, it comes to be approximate 1334 units. C with 32,000 units per year, by applying same formula, it comes 896 units. D 1 lakh units per year, by applying the same formula, that is root 2ds upon H into root P upon P minus D, it comes to be 824 units. Calculation of EOQ. Q equal to root of 2ds upon H equal to root 2 into 6400 into 100 upon 2 equal to 800 units. Number of units ordered per batch remains same as estimation of optimum batch size by applying EOQ model is independent of number of units produced per year or in a given time period. This provides us two important differences between EOQ and EPQ model. EOQ model assumes number of units produced in given time period to be constant, whereas in EPQ model it can vary during that time period. The above results does indicate that with increase in number of units produced per year, batch size Q of each order keeps decreasing, implying an inverse relation between batch size and number of units produced per year in EPQ model, whereas batch size in EOQ remains same. A case of EPQ. As discussed in earlier sections, economic production quantity EPQ model consists of two sections. The first section is termed as production phase, wherein following three activities are performed. Production P at a constant rate, consumption or daily demand at constant rate. Because of the assumption of production rate being greater than consumption rate, that is P greater than D, there would always be replenishment of the product. A case of EPQ continued. The second section is termed as non-production phase, wherein following two activities are performed. As required production quantity has been achieved, so there is only consumption at constant rate. As there is no production, so there would only be depletion of quantity produced. This has been illustrated in following example. A bottling plant undergoes the process of filling a particular cold drink. The process involves three steps. In first step, the used and emptied bottles are cleaned. Then in second step, as the bottles gets cleaned, they are stored in warehouse. Lastly, bottles get into production process of filling the drink. The filling machine, according to its capacity, takes empty and clean bottles and fill it. So process of filling bottles from cleaning, then store, then filling. The production phase involves all three activities, whereas non-production phase involves only activities of storing and filling. The production process has the capacity of producing 4,000 hectares liters per month. 25% of the production is filled into cleaned bottles. 8,000 bottles are cleaned on the cleaning line per day. Further, following data is given. Annual demand D equal to 1,20,000 cases per day. Production rate 1,46,000 cases per day. Annual holding cost 20 units per case. Setup cost 12,000 unit per case. By using this data, the company intends to find out following inventory parameters in the endeavor of minimizing total cost. What is optimum lot size? What is maximum inventory level? What is the minimum total annual cost? Time period for production phase. Time period for non-production phase. Now optimum lot size can be calculated by using the formula Q equal to root of 2 ds upon h into root of P divided by P minus D. Now putting the values Q equal to root of 2 into 1,20,000 into 12,000 upon 20 into root of 1,46,000 divided by 1,46,000 minus 1,20,000 equal to 28436 units. Maximum inventory level can be calculated as I max equal to P minus D upon P into Q, that is 1,46,000 minus 1,20,000 upon 1,20,000 into 28436 equal to 5064 units. Minimum total annual cost can be calculated as total cost TC equal to root of 2 into Q into H into S into root of P minus D upon P equal to root of 2 into 28436 into 20 into 12,000 into root of 1,46,000 minus. So students, let's now summarize what we have learned in this module. Economic production quantity or EPQ model computes optimum batch size that should be ordered, incurring minimum possible cost with production and usage of a particular product occurs at same time. It is different from EOQ model where replenishment was done in batches and only consumption used to happen without any concerns to production. The chapter discussed assumptions and model of EPQ. Also, computation of optimum batch size was discussed under two cases. Case 1 highlighted the scenario when production happened for part of ordering cycle, whereas case 2 production and consumption occurred simultaneously for other ordering cycle. Also, differences between EOQ and EPQ were illustrated through an example. It was found that EOQ is independent of number of units produced where EPQ is not. Thank you.